All right, we're going to learn about atoms, elements, compounds, and mixtures, which are all obviously matter. So we talked about the different states of matter, the properties of a solid, liquid, and a gas, but now we're just going to talk about what different states those can exist in. So the first thing we're going to talk about is a mixture. So a mixture is a physical blend of two substances. So that part where it says physical blend, that's the sign that it's not chemically combined. Okay, so this would just be something physical that happens. Classified as either homogeneous or heterogeneous. All right, so there's two main types of mixtures, and these are the types. A heterogeneous mixture is one in which the composition is not uniform throughout. All right, so the way that I usually describe this, if it's not uniform throughout, if I poured it into a beaker and I took a sample from the top of the mixture, the middle part of the mixture, the bottom part of the mixture, it would not necessarily be exactly the same. So not uniform throughout. So some examples listed here are chicken noodle soup. Okay, so obviously there's different components to that. It's not the same. You're not going to get the same spoonful every single time. And then wet sand would also be a good example. So wet sand, the water is obviously going to sink to the bottom, but the top part is still wet, but not necessarily, doesn't have as much water as the bottom portion. The next type of mixture is a homogeneous mixture. So this is a mixture that does have a uniform composition throughout. Okay, so homogeneous, there is a uniform composition throughout. So this would be the same. If you put it in a beaker, took a sample from the top, the middle, and the bottom, this material would be, every sample would look very similar. So an example here, or some examples here would be sweat. So kind of gross, but thinking about a beaker full of sweat, but it would be uniform throughout. And then tea with sugar. So the one example, I guess the one change that I'd say with tea with sugar would be to make sure that the sugar is like totally dissolved. Because if you want it to be the same throughout, that sugar can't be sitting at the bottom. All right, so we are able to separate mixtures by using physical processes. Again, the idea of a mixture is that it's not chemically combined. So that means that when you want to separate it, you also don't need chemical processes. So an example, or here's many techniques that they say you can take, that you can separate a mixture if you use these. So an example would be filtration. So let's say I have a mixture of like sand and water. I can filter out the sand particles by filtering. Distillation, which is a separation by boiling point. So that would be, let's say that I have a mixture of water and ethanol. Ethanol has a significantly lower boiling point than water. So I can actually distill. So like I could start heating up those liquids that are mixed together, and the ethanol portion of the mixture will evaporate or just condense and then recollect in a different, in a different beaker or whatever you want to call it, because it will evaporate before the water does. So that's how we can separate that. We could centrifuge something, which is a separation by density. So centrifuging is just like spinning a sample. So you may have seen these on like CSI shows or something. But they have these like tiny, tiny little test tubes. And if they spin samples fast enough, maybe like particles of a solid or something would sink to the bottom, and then liquid could go to the top. So they actually do this with our blood whenever they take it. You may have seen like samples of blood that have been like sitting out maybe on your doctor's counter. So these always have like the plasma at the top. So it's like that like clearish yellow liquid, and then the red blood cell part near the bottom. And then chromatography is a separation by polarity or solubility. So an example of this would be if you take like a piece of paper towel, put a black marker dot on it, and you let water kind of carry, you dip the paper towel in water, those particles will separate based on size. So black is composed of different colors that help make that color look black. And so when you actually dip that paper towel in water, it's going to help the different colors separate out. And they separate because of their polarities and solubilities. Some of the colors will travel further, some of them won't. But those are just some examples of separating mixtures. And again, all of these processes that I just discussed are physical processes. All right, so now we can talk about pure substances. So a pure substance has a fixed composition, which means it won't change its chemical formula, and you cannot break it down into simpler substances using physical processes. All right, so if we're talking about, so there's two kinds of pure substances. All right, the first kind is an element. So this is the simplest form of matter that you cannot chemically break down into smaller substances. So if something is an element, it only consists of one type of atom off of the periodic table. All right, so maybe I will add that note, one type of atom. All right, then a compound is when two or more different elements are chemically combined into a fixed proportion. Right, so chemically combined means, again, you cannot separate it by a physical process like what the definition of a pure substance is. And a fixed proportion just means that it's always in a specific ratio. So for example, you've probably heard of salt, which is NaCl. All right, so this ratio says that there's one sodium atom for every one chlorine atom. If something had a different proportion, then we wouldn't call it salt. Okay, it'd be something different. Right, same thing with water, okay, H2O. There's more than one element because they see hydrogen and oxygen. But if I changed this number of hydrogens, or if I added a number here or changed, a number from being one, which is what it is right now, it actually wouldn't be water anymore. Right, so that's the idea of fixed proportions. You cannot change those little numbers. You can't change how many atoms ratio to the other type of atom. All right, so compounds are made of elements. Yes, we just went over that example. And compounds can be broken down by chemical means into elements. Okay, but not physical. So I can't just take NaCl, salt, dissolve it in water, and boil it off, and all of a sudden I don't have salt anymore. That's not going to happen because remember, boiling and vaporization are physical processes. So that's not going to separate it. Same thing with water. I can't separate the hydrogen and the oxygen from each other just by boiling or freezing or melting or doing anything like that, because again, those are all physical processes. I can separate them by using maybe a chemical reaction or applying an electric current, something that is a chemical means, not a physical means. All right, so some more definitions. So we just talked about atoms and elements, and remember, atoms and elements are those pure substances. So an atom is a building block of matter. We know it's the smallest unit, and we're going to talk about the subatomic particles later on. An element is a substance that is made up of entirely of one kind of atom. So again, this would just be like anytime something is an element, it's made of one element, one box on the periodic table. All right, and a molecule is when you have two or more atoms joined together chemically. All right, so we're going to talk about diatomic molecules below, but again, two or more atoms that are joined together chemically. So an example could be like oxygen, like you've probably never heard of oxygen just as O, you've probably heard of it as O2. All right, so that's an example of a molecule. So there's two or more atoms joined together. Compound like we talked about on the previous slide, is when we have two or more different atoms joined together chemically. And again, can't separate it by just boiling or freezing or melting. It has to be separated using chemical means because the atoms are joined together chemically. All right, so we have some diatomic molecules. And like we talked about here, a molecule is when you have two or more atoms joined together chemically. So on the periodic table, we have 7 elements in the table that exist in nature as diatomic molecules. All right, so you're probably seeing this di and you're thinking 2, which is exactly right. So these are 2 atom molecules. These 7 elements are never found as atoms by themselves. They're always found as these paired molecules. So here's an example, like they have pictures of this like nitrogen and oxygen, and notice how each one of those has 2 atoms kind of stuck together. Okay, so all of these elements are still considered, all of these, I guess, molecules are still considered elements, even if they exist as pairs, because they're made up of only one kind of atom. All right, so here are those 7 diatomic elements. So we've got hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So they kind of form like this number 7 on the table, and then you just have to remember that hydrogen is all by itself on the left-hand side. The other way to remember this is Hunkelbrief. It's a made-up word, but this is still how I remember it because this is how my chem teacher taught me. Hunkelbrief. So it's just, again, these same 7 elements, but a way to help you remember that these are the diatomic elements. Now, you know that whenever someone is talking about one of these, you're never going to just have the letter. It's always going to be the letter 2. Okay, they always exist as pairs. So like I would never say hydrogen and just write H. I'd always write H2. Just like I wouldn't say chlorine gas and just write Cl. I'd always write Cl2. Because, again, these in nature never exist as solo atoms. They're always going to exist as pairs. All right, so here we have kind of a nice little chart to help you classify matter according to its composition. And we can describe it again as either an element, compound, or a mixture. So first step, so does it have a variable composition? If the composition is not the same throughout, then we have a pure substance. Can we separate it into simpler substances? If not, then we have an element. And if we can separate it into simpler substances, then we have a compound. If we answer yes to the variable composition part, then we have a mixture. If it's uniform throughout, remember that's called a homogeneous mixture. And if it's not uniform throughout, a heterogeneous mixture. And if we take a look at those particle pictures, so helium, remember that's just an element. And again, an element means that it's only made up of one kind of atom. So here it's labeled helium, so that's only one kind of atom. In the next one, for pure water, we do see a ton of water molecules, but that could be a compound. All right, here we have our mixture of wet sand. So we know that this is sand and water. So take a look here. It looks like these are different. The ones at the bottom are like a different color than the top ones. So it looks like the sand part is at the bottom and the water part's at the top. Again, the whole definition of a heterogeneous mixture is that it's not uniform throughout. So it's not the same throughout. So this would be, again, example of a heterogeneous mixture. A homogeneous mixture, so here we have tea with sugar. So we've got, I see some water, I see maybe some sugar molecules, and I think this is the same thing, just kind of turned around backwards. So again, this is considered homogeneous because these are evenly spread throughout this whole mixture or throughout the whole liquid. If all of these had like sunk to the bottom, like I mentioned before, with like maybe sugar that didn't dissolve all the way, then that would not be homogeneous. But since these are dissolved and there's no like sugar sitting at the bottom, these are kind of like equally spaced apart, that would be homogeneous. All right, so let's take a look. Classify each of the following substances as either pure or a mixture. All right, so remember, pure substances are either elements or compounds. All right, then if we have a mixture, we can describe it as either being homogeneous or heterogeneous. All right, so if we take a look, aluminum, so pure or a mixture. Again, pure is either an element or a compound. Aluminum has its own box on the periodic table. It is an element. All right, so first it's pure, and it is an element. All right, apple juice. Definitely not on the periodic table, so it's maybe not an element, and there's no like chemical formula for apple juice. So we know that it's going to be a mixture. All right, and the type of mixture, usually, and I've never seen this, I guess, usually apple juice is pretty clear. If you have a glass of apple juice and you take a sample from the middle, the bottom, and the top, they should all be the same. So we're going to call this a homogeneous mixture. All right, so the next one, we have hydrogen peroxide. Ooh, and then they gave us a formula, which was really nice, because you may have not known that was the formula for hydrogen peroxide. So like the stuff in the brown bottle that you may have put on like cuts before. So H2O2. Well, there's a chemical formula for it. And I can see that there's more than one element involved in it. So this is going to be a compound. It's pure, because I see that it is composed of just those two elements, right? And it is a compound because it's more than one element present. All right, then the last one, beef stew. I don't see a chemical formula there, so I don't have something pure, but I do see, I know what beef stew looks like, and definitely looks like a mixture. Right, and in terms of homogeneous or heterogeneous, not the same throughout. You could take a sample from like different parts of the beef stew. Not every single part of it is going to be the same, and you can see like the meat pieces, the veggies, and whatever else. But it's not exactly the same throughout. So this is heterogeneous. I think I spelled that wrong, but you know what I mean. All right, so if you're interested in watching what's in a molecule, they talk a little bit about how macaroni salad is made up of like so many different things depending on, whatever the components are. So thinking about how like a compound can be so different than the elements that make it up. Okay, which is what this statement right here says. It says the properties of compounds are often very different than the properties of the elements that make them up. All right, so here's what like an example of that. Water. You guys are all super familiar with water. At room temp, water is a liquid. It is not flammable. Right, and those are basically the two properties I kind of wanted to talk about. Now, the elements that make up water are very different. All right, so we can see that we've got hydrogen that makes up water, and then oxygen. Remember, it's diatomic, so it also makes up water. When these guys are not in the chemical compound of water, of H2O, these guys exist as gases. So this is a gas at room temp. Right, and I don't know if you guys know much about it, but these guys are highly flammable. So hydrogen gas, very flammable. Oops. All right, same thing with oxygen gas, very flammable. All right, right, so that's just one example of how elements that make up compounds behave or act really differently and have different properties than when they are actually combined in the compound. Okay, so it has nothing, once they combine and once they change their chemical formula, okay, again, just based off of, forming whatever compound, they get very different properties.